Hi guys, welcome back to another video of me teaching, and today I have this integral on the board for you guys. So why don't we just get into the question? Well, let's look at this integral. I'm going to show you two methods to solve this. The first method you probably would have thought of by now is integration by parts, which is one of the typical ways to solve this. Method 2 is where the fanciness gets. It involves having complex numbers. So why don't we first try method 1, which is integration by parts. Well, as you might already know, you can just put this e to the ax into the differential. So this will just be equal to the integral of cosine of bx times d e to the ax. And because of the chain rule, you need to multiply the outside by 1 over a. So now we can use integration by parts. So this is equal to 1 over a times this times that, which is cosine of bx e to the ax. And then we have to subtract the integral. This multiplied the derivative of this. So e to the ax multiplied by the derivative of cosine bx. So if we solve this, then it will be 1 over a times cosine of bx e to the ax, then minus the derivative of this is just negative b sine of bx. So then this negative and this negative will become plus integral e to the ax sine of bx. But because of the chain rule, you have to multiply by b dx. So now I'll first expand this part. So it will be 1 over a cosine of bx e to the ax plus b over a times. So if we do integration by parts again, we have to do the same thing, times integral sine of bx d e to the ax. Because of chain rule, we have to multiply by 1 over a on the outside. So again, this will be 1 over a cosine of bx e to the ax, then plus this is just b over a squared times the integral of, we have to do integration by parts, so it's not integral anymore. To do a big bracket. So we first do this times that, which is e to the ax sine of bx, and then minus. If you do this on your own, you can do this times the derivative of this. Then you'll find out that it will just be b times the integral from e to the ax times cosine of bx dx. So this is just equal to 1 over a cosine of bx times e to the ax, then plus this times that is just b over a squared times e to the ax sine of bx. Then we subtract this times that is just b squared over a squared times this is actually just I. So multiplied by I. So we know that I is actually just equal to this. So if I rub everything out, so if we move this to the left hand side, then we can see that a squared plus b squared over a squared times I is equal to, if we combine these using the common fraction, then this becomes a squared and this is a. So if we add them up, then it'll be, the top is a times ex cosine bx. So ax cosine bx. And then we add it with beax sine bx. And the bottom is just a squared. So the first thing we can notice is this and this cancel out. And then we can just divide this. So we can see that I is equal to, we can also factor out a e to the ax. So the inside just becomes a cosine of bx plus b sine of bx. And the bottom is a squared plus b squared. Done. So this is method 1. Now I'm going to show you method 2. So method 2 will involve complex numbers. Why? Because we can see that in the integrand, there are two main concepts of complex numbers. First of all is e to the something x. And second of all, we have cosine and maybe sine. So this lets us think, what if this is just part of a complex number? So don't we just need to add the imaginary part? Yes, but wouldn't that make it more complicated? Actually, it will not, because we'll end up with a very simple integral. And when we solve that integral, we will get a complex number. And if we separate that complex number into its real and imaginary parts, we just have to equate the coefficients by saying that this real part is just equal to the solution's real part. So that's what we're going to do. So if I rewrite this to be, still, I'm going to copy this, but we're actually going to add an imaginary part. So we add I times e to the ax times sine of bx dx. Okay, now what do we do? Well, obviously, can't we multiply the I inside? And then can we multiply can we add up the integrands? Then can we factor out the e to the ax? Yes, so that's what I'm going to do. So this is equal to one big integral e to the ax multiplied by cosine of bx plus I sine of bx dx. And now this is a typical integral, and we can simplify this even further to make it in this form. So this is just equal to the integral e to the ax multiplied by e to the, well, we need I times theta, which is the bx. So times I bx dx. So if we have multiplication of two powers, we can just add them up. So this is equal to the integral of e to the power of ax plus I bx dx. So this is equal to e to the power of, we can take x out, so the inside is a plus bi times x. And now this is a super easy integral, because a plus bi is just a constant. So we can use the reverse chain rule. So this will be, because of the reverse chain rule, we need to multiply by 1 over a plus bi times e to the a plus bi times x. So now we need to, since this is the solution, we need to separate it into its real and imaginary parts. The first step in doing that is we are going to change this back into this. So this will become 1 over a plus bi times e to the power of ax times e to the power of I bx. And then we're going to do a realization, which means that we multiply the denominator by its conjugate, which is a minus bi. So this is equal to, the bottom, if you work it out, would be a squared plus b squared and the top is a minus bi. Don't forget to multiply by e to the ax times e to the I bx. Okay, so now we are actually going to change this back into this. So if I club everything out, so this will be a minus bi, a squared plus b squared times e to the ax bracket. This is just cosine of bx plus I sine of bx. Now I can work. So as we can see, this denominator is real and this is real. So we can put this and that into one group. And then we can multiply this thing by this. So I'm basically saying that we can put this to the numerator and we multiply this into this bracket. So this will be a squared plus b squared on the bottom, then e to the ax, then multiply by that time this thing times that is just a cosine of bx, and then minus ib cosine of bx. Then we do this bracket times that, so it will be plus ia sine of bx. Then we see that there's an I and an I here. So it will be minus I squared, which is minus negative 1, which is positive. So we have to do plus b sine of bx. So this is equal to e to the ax over a squared plus b squared times, okay, so we see that this and this is the real part. So we can multiply this by a cosine of bx plus b sine of bx. So this is actually just all of the real part. So we have actually already solved this I, which is this. And you can double check, it is the same answer as we got when we did integration by parts. But to make this proof more concise, we can't say it's just equal to this. We still have to write out the imaginary part. So we add I times e to the ax multiply by a sine of bx minus b cosine of bx over a squared plus b squared. So we know that I is actually just this part. Done. Well, you guys might have noticed that I didn't write the plus c in both of these integrals because I thought that it might be a bit more complicated with this random plus c. So to make you guys happy, I'm just going to write a small plus c over here. So this is the final answer to this super fun integral which uses two methods to solve. So thank you guys so much for watching, and if you enjoy my videos and you want more videos like this, please consider liking and subscribing. If you want to master something, teach it.